We were working in section 3.1 last time, and we had gone through several numeration systems. Wow, that's really dark, isn't it? Let's try that today. Okay, several numeration systems. The Egyptians, and we decided that if we had to write numbers that had lots of 8s and 9s in them, that's not super convenient. We did the Babylonians, and we decided, man, not having a 0 makes it tough, right? Who was next? The Mayans, right? The Mayans had a 0, so that's kind of cool, but we still have the problem with the dots and the lines potentially looking like the same place value because we have no sort of like commas or separation abilities very well. We also probably didn't like very much that it wasn't a true base 20 system, right? There was this arbitrary like times 18 thrown in at one place, and it felt like, well, that's kind of awkward. So we have another system today that we're going to look at. This is the Roman numeration system. Of all the systems that we've looked at, this is one where we still see it actually used today. So where have you seen the Roman numeration system used in everyday real stuff today? In notes, okay, so like outline forms of things, that's one, good.
I see it on clocks. My parents always had a clock with Roman numerals on it.
Okay, so we'll see it on clocks or watch faces still sometimes, yep. Anywhere else? Okay, so like suffixes. I was like, this is subscript. That's not the right one. Suffixes. Thank you. Suffixes on names. Yep. There's somewhere else you've seen it, probably more recently than you remember. You'll often see it on sporting events, like Super Bowls, Olympics, things like that. Yep. And another place is if you do travel, if you ever go to any of the historical things, like on the East Coast, you'll see it on buildings, establishment dates, things like that, still on Roman numerals on those buildings. So there's actually quite a few places we still see this in use today. We don't see it in use in the sense of actually doing mathematics with it, so that's something that's not really what we see, but we do see it used. So let's see if you remember. I know you'll remember some of these for sure, but maybe you don't remember all of them. The values for the different Roman numerals. So these are the different Roman numerals. How much is the first one, the Roman numeral I, worth? It's worth 1. Whoops, hang on. There we go. How about the V? That's 5. X? L? That's 50. Yeah, at that point we start going like, wait a minute, I don't see those used as much. And it's true, we don't, but C, 100. Even if you're not sure on these, do you see a pattern going on in my list of numbers over here? Okay, so using the pattern then, what do you think D would be? 500. And M is 1,000. Okay, so very good. These are the different Roman numerals, and there is a way, and I will show you how to make a number bigger than this. We do have that at our disposal as well. And they do, in fact, avoid one of the issues we saw with the Egyptians where they wrote the numerals out like a bunch of times, and we said, I don't want to write a lot of 8s and 9s, remember? They have a way that they avoid some of that repetition, too. So let's take a look at a couple of the properties that they have. The first property that they have is the subtraction property. To avoid repeating a symbol more than 3 times, that's the magic number, no more than 3 of the symbol, a smaller value is placed in front of a larger one. But you can't just put any smaller value in front of any larger one. It doesn't work like that. Only one value smaller may appear before a larger value. So, in particular, what this means is that when you have 4s and 9s, this property is used. So if your value has not got 4s or 9s, it's not going to use the subtraction property. For example, if you wanted to write the number 90, okay? So the number 90, if you were to try to write it out with their numerals, with 50s and 10s, you would have to write 150 and then 4 10s. Agreed? Okay, but we don't write digits 4 times. That's sort of one of their properties. They don't write them 4 times. So what do they do instead? Well, instead what they would do is they would write the number 100. So what was the number 100? C. And in front of a C, you're allowed to put one digit smaller. So here's my C, and it's this one right here that you're allowed to put in front of it. A 10. That's one place value smaller, like place value the way we do it in our system, okay? So you're allowed to put a 10 in front of a 100. So what's the value for 10? X. So if you put an X, a smaller value, in front of a C, the larger value, this is the subtraction property. 10's in front of 100, this would be the number 90. Okay? Now, on the flip side, you can't do that with 99. Like, it would be really nice if you did 99 to put a 1 in front of a 100, wouldn't it? But a 1 is not one place value smaller. It's two place values smaller, right? It's got one digit instead of 3. So we don't have that property with the 99. So we have to think about 99 instead as 90 plus 9. And we do the 90 the same way we just did. How do we do 90? XC. How do we do 9? You probably just remember that one. IX. Right, so over here with the 9, you'd take the 10, and then one place value smaller is the 1, so IX would be the number 9. So 99, unfortunately, is not IC. Whoops. But it is XCIX. Okay? So that's how we deal with the subtraction property for the Roman numeration system. The multiplication property also shows up. This has to do with getting numbers that are larger. Okay? So a bar is placed over a Roman numeral to multiply it by 1,000, and a double bar multiplies by the number 1,000,000. So if you wanted to do the number 9,000, in essence you would be doing the number 9, and then we're going to have thousands, and the way that we're going to get thousands is we're going to put a bar on top of things. So let's start with the 9. How do I get a 9? IX. And I put a bar on top of it, not touching it, not like when we, just like run them together, but above it. Okay, a bar above it means times 1,000. And if I put 2 bars like this would be the number 9,000,000. Okay, so that's not answering my question. I just want you to recognize. A double bar on top is times 1,000,000. A single bar on top is times 1,000. Okay, so that's maybe a property you've never seen used before for the Roman numerals. And that's probably because what we use Roman numerals for today is not for large numbers, is it? Not so much. Okay, so we're going to do some examples in the Roman numeration system. First, we're going to consider the number MCMX. Now, it's important to recognize places where it changes from small to large. So M, I know we can actually write down the numbers, and we will do that in a minute, but M is 1,000, right? C is 100, and then M is 1,000, so C coming before M is going to be a subtraction property. But then the X at the end means that we end this number with 10. So far, so good. All right. What Roman numeral will come before MCMX? Okay, so you would include an I, and the I would actually be before the X, because we want to take the 10 and we want to make it a 9. Okay, so instead of the number ending in 10, the number now ends in 9. What would be the numeral that comes after this value? Right, the I would actually be on the end, so it would be XI. Again, because we want the numeral to end in 11 now instead of 10. Right? XI is the number 11. Okay, so now let's actually figure out what the number is in our system. So we have M. We already said the C and the M sort of go together because it's smaller in front of larger. And then we have the X. So the M is 1,000. C is 100. And the M is 1,000. So what happens when we have 100 before 1,000? You subtract to give me what, Sally? 900. And then the X at the end is 10. So this is 1,000, and then it's a 900, and then it's a 10. So what value do we have? 1,910 looks a lot like a date, which it would be like on a building or something like that potentially, right? 1910. Okay, so we're going to go the other direction, just like we have with the other numeration systems. We have 1,492,019. Okay, so it's a big number, right? So as soon as you see big number, you should be thinking, I'm going to do those bars. I don't know how many bars yet, but there's definitely going to be some bars involved because this is the number, it's a 1 million. It's a big number. Now, in particular, it's kind of nice because the commas that they use, or that we use, can break things apart really well. So right here, the number 19 at the end is going to just be written like a 19. There's no bars on that part. But the number in front, 1,492, I know it's 1 millions, but that number where it breaks apart, that's going to be the part that has the bar over it. Okay? So let's do the 19 first, just because it's at the end and it's not going to have any bars. So how would I do a 19 in their number system? Close. XIX. Yeah, so the first X is the 10 in the 19, like the tens digit, the 1 there, okay? And then the IX is 9. So I get this one by X, and this one is IX. Okay? There's no bars on the top of it. It's just standalone at the end of the problem. All right, now if I ignored the fact of where it is, the number 1,492, that part of it, I could write with just regular old Roman numerals, right? The fact that it's in the millions place and in the thousands place we'll deal with the bars. So let's just write down what we would get for 1492, which is when Columbus sailed the ocean blue, right? Yeah, okay. All right, so how do I get the 1,000 part? That's an M. How do I get the 400? Okay, so 4s and 9s are special, right? How do I get 400? A C and a D. So C is worth 100. We encountered it before. What's D worth? 500. So a 100 before a 500 would be 400. Everybody good with that? 100 before 500 is the 400. Okay, how do we get 90? We did that already. X and then C. I'm going to move this over just a little bit. Okay, XC is 90, right? 10 before 100. And then the 2 is the 2 I's. And if I leave the number like that, that's the number 1,492. But I don't have 1,492. I have 1,492,000, right? So I need a single bar on top of this whole thing. Because a single bar on top of that 1492 will take 1,492 and multiply it by 1,000. Well, multiplying it by 1,000 moves it over into the exact location that it is in our number, in the 1 millions place. Okay? So in other words, if I were to multiply 1492 by 1,000, I would end up with 1,492,000. And then this part right here is put in with the XIX I have at the end. Okay? So that's where that's coming from. And then we can scoot this over. We don't need the XIX sort of, bigger and a little further away or whatever. Okay, that was weird. Now it's crooked. There we go. That's better. So this would be my answer in Roman numerals. Okay, so it's a little longer than our number, right? But it's not like crazy longer. It's not like it would have been if we were working with the Egyptian system where we repeated a digit 9 times or something, right? It's not that bad. All right, and obviously I forgot to bring something because that's what happens. I had forgotten this was in this section, base 10 blocks, but we'll talk about it anyway. I know you've seen base 10 blocks before, whether you remember it at this exact moment or not, Let me describe to you what base 10 blocks look like. They're physical manipulatives that you can use to show kids how to add in base systems like ours, where we have a place value system, base 10. Okay? So you always have a units block, and it's usually one little square. And then sometimes even they break apart and they stick back together kind of like Legos. And if you stick 10 of them together, you have one that's 10 long, and it's called a long because it's long. I know it's a super unique name right there, right? Long. It's a long. And then if you were to stick 10 longs together, you end up with something that's called a flat, and it's big, square. And so basically, this is 10. That's a 0. 10 by 10. Okay? And this is just 10 long over here. So you have a flat. And then if you put 10 flats together, you have what's called a block. So it's a three-dimensional object. I know my sizes don't quite match up here, but imagine for a sec. All right, so this isn't perfect, but... All right, so it looks something like this. It's 10 long, 10 wide, and 10 tall. 10 by 10 by 10. Like that. Okay. I'll bring them next time. Don't use the word try, because then you forget things. I will bring my base 10 blocks next time just to show you. I have them, they're red and they're plastic, okay? One of the things base 10 blocks do, and money does this too, except base 10 blocks are kind of nice because they size-wise compare for us really well, is they show kids why a 9 in the tens place is not the same as a 9 in the hundreds place. The sizes are different, right? 9 in the tens place is 9 of these long pieces, but a 9 in the flats place is 9 of these flats that are square and big, okay? They also show how you can combine things, you know, so I can't combine a long and a flat because they're not the same size. They're not alike. So they have a very nice concrete feel to them visually. Now, it's all based on base 10 because that's a base system that we used. But I mentioned this the last time, that part of today's class period and the material that we're looking at in this class period is going to make you feel uncomfortable because it's not what you're used to. And no, it's not something you teach in schools. That's not the point. The point is to give you some of that uncomfortable feel so that when you teach kids, you can remember, oh yeah, I remember how it was to add in base 7. I don't like base 7. I don't use base 7 all the time. It doesn't work for me, right? Because I don't use it. Well, that's how kids feel when they first start working in base 10. They're not comfortable that they don't know it. They don't work with it all the time because they just haven't yet. And so it's sort of give us that perspective. So let's take a minute to think about base 8. We talked about base 8 last time, right? It's the base system we would use if God did not give us thumbs, right? Because we'd have 8 fingers, okay? So a base 8 system, well, in base 10, everything is based on pushing 10 of these objects together. Well, in base 8, it's going to be based on putting how many objects together? 8. So in base 8, we're going to have a unit. A unit is always worth 1. How much would a long be worth? It'd be worth 8. What would a flat be worth? 64. It'd be worth 8 squared, which is 64. And how about a block? It'd be worth 5 cubed, which is what, Sally? 512. So if you had manipulatives where you had 2, 3, 7, okay, the 7 is in the units place, the 3 is in the longs place, and the 2 is in the flats place. What would it be worth? How many individual blocks would there be if you sort of counted all of them? So how could I figure this out? How much would I really have if I had, for example, 2 flats?
64 times 2.
Right. I have 2, and they're each worth 64. And I have 3 longs. So I'd have 3 times 8. And then units are the same no matter what system you're in, so you have plus 7 units. So if I add up 2 times 64 plus 3 times 8 plus 7, and feel free to grab your calculator, you're going to want it today, how much would this be? 159. That's how many individual blocks you'd have if these were like Legos and you could break them all apart. There'd be 159 of them. I put a note in here because you're going to see some questions written the same way that this note sort of gives you a heads up for. Question B above is equivalent to asking what would 237 base 8 be when written as a base 10 number. Okay, it's the same question. Asking what is it as it's written as a base 10 number is the same as asking if I took this weird system and I broke them all apart into its individual unit components, how many of them in my number system would I have? And the answer would be 159 for this particular problem. So what we're going to do next is we're going to think about and talk about different number systems. So the first number system that we're going to look at is base 3. Okay? Now, I'd like for you to think about, before we do that actually, base 10. We've mentioned this, we didn't write it down, but we've mentioned this. We have 10 numerals in base 10. What are they? 0 through 9. So there's not a numeral for 10 in base 10, right? It takes 2 numerals, the 1 and the 0, to give me a 10 in base 10. So in base 3, we're going to have a 0. And then what do you suppose we're going to have after 0? A 1. And then a 2. Am I going to have a 3? No. There will be 3 numerals in base 3, and I've already written them down. So what do we do in base 10 when we run out of single-digit numbers? We make double-digit numbers, and what's our smallest double-digit number? 10. It's a 1 followed by a 0, right? So the smallest double-digit number in base 3 is also going to be a 1 followed by a 0. We're not going to say 10, because that's how we think about it in base 10. We're going to say 1, 0. What would come after 1, 0? 1, 1. And then 1, 2. What would be next? 2, 0, because there is no 1, 3, because there is no 3, right? So after 1, 2 would come 2, 0, and then 2, 1, and then 2, 2, and then what happens? We got to get to the 3-digit numbers. So the next thing that would happen is that we go to 1, 0, 0. Okay, and we could keep going with this, right? This is an infinite process, just like it is when a child starts like, I can count to 1,000,000, and you're like, well, no, you can't. But conceptually, you understand how, right? We could keep going with this conceptually indefinitely, right? We could keep going forever, quote unquote. All right, so what would happen if we want to use base 7? You'd go from 0 to 6. But there would be no 7 in base 7, nor an 8 or a 9, right? You'd have to stop. What would come after 1, 6, or after the 6? 1, 0. And then you'd go up to what?
1, 6.
Right, 1, 6. And then we would keep going, right? And then what's after 1, 6? 2, 0. I'll write that one in, and then I'll put a dot, 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 okay? All right, so what happens when I say base 12? How is that different than the last 2 questions? Yeah, so you guys are all saying it, but you're not using the words that I was thinking. The words I was thinking is it's bigger than 10 instead of being smaller than 10, right? There's something about it that feels like I need more digits. I don't just get to stop with the digits like I did on the base 3 and the base 7. I just sort of threw the extra ones away. Somehow I need more. I need my own 2-digit numbers already or something like that. So what do I do? Well, let me show you what your book does. I'll talk to you about what other textbooks or other resources as well do too, just so that you're aware. But we start with 0 and we go up to 9 because we need all of those. But as some of you were saying, I need a 10 and I need an 11, right? There's no 12 because it's base 12, but I need a 10 and I need an 11. But I can't let 10 be 1, 0 because that's a 2-digit number, right? I got to have something else. So what your book does for 10 is it calls it T, and for 11 it calls it E. That's what it does. It's not my favorite. Another resource that I've used before, you want to know, it does A, B. I like that much better. It goes A's and then B and then C and then D if you needed more digits and bigger value systems. That's what it does. But this one does T for 10, E for 11. If you were working in, say, base 14 and you needed a 12, it would do W for 12. I don't know what it does for 13. We're not going to get too big in this process. The goal is not to confuse the letters with the numbers and so forth. But T is 10, E is 11. Okay? All right, so let's think. What would we do after 11 then? 1, 0. And we'd go all the way up to 1, 9. And what do you suppose we would do after 1, 9? 1 T. And then 1 E. And then what would be after 1 E? 2, 0. Right? Now eventually this will get large enough that you would have the biggest 2-digit number. What would the biggest 2-digit number be in base 12? Double E. Good job. Yeah, E, E.
Is that why the calculator has the double E?
No. The double E is like that in your calculator for scientific notation. Yeah. Good question, though, because it does show up that way there. All right, so EE would be our biggest 2-digit number in base 12. And then after EE, we would have our smallest 3-digit number, which would still be 100. Yeah. Okay, and then the process would continue. Okay, so thinking about those 2-digit, 3-digit numbers and so forth in other number systems. Okay, so just like we did with the other base systems, where we're starting right here is writing the number that comes before and the number that comes after a certain number in a certain base system. So right now, this is the base system 5. So what would be preceding? That is, what would come before the 1, 4 in base 5? And then what would come after? So what comes before 1, 4? 1, 3. And we are going to write subscript next to it representing what base system we're in. This is 1, 3, base 5. And the way that your book does it, and I think this is very common, is to write the word as the subscript. So it writes the word 5 down there, okay? It's a very common way to do that. What would come after 1, 4? 2, 0. Yes, it would. So it would come 2, 0, base 5. Sometimes they will do this, like that. I tend to not like that notation quite as well because sometimes those subscripts start to look more like they're right next to it and look like multiplication. So this is not my favorite notation, but you're right. Some resources will do that. Okay. Okay, we're going to do the same thing in base 12 now. Okay. So in base 12, we have a number that's before, then we have T, 0, 0, right? Base 12. And then we have a number that comes after. Okay, so the numbers that I picked are because either the before or the after is weird, okay? In this case, the after is perfectly easy. What is after T, 0, 0? T01. So there's nothing really sort of enlightening about this. It's T01. Okay, so T01, 12. That's easy. But the number that comes before it is weird. What would come before T00? It's 9 double E. Okay, so Hannah's the one that got it right, that thought it through correctly. So can you explain, Hannah, why you came up with, or how you came up with 9 double E, 9EE?
Because 9 is the digit less than T, and then...
Okay, so the first thing she did basically is she decreased the first digit by 1. Okay, so the number that comes before T is 9. And then what?
The greatest digit is 12. That would come before starting over with 0.
Yeah. And if it helps you, you can think about our number system. If you had the number 800, you decrease the 8 by 1, right? That's what Hannah did. She decreased the first digit, the T, by 1. And then the 0, 0 is the biggest digit possible in the place values after that. And our biggest digits would be 9s, right? So it'd be 799. Well, the biggest digit in base 12 is E, so it's 9EE. That's what's happening there, okay? All right, the next thing we're going to do is we're actually going to convert numbers in and out of our number system. The first way that we're going to convert is we're going to convert into base 10. So converting base blank, whatever that blank is, into base 10. And what I want you to write down here is the key is to multiply. I would strongly encourage you that when we get to the point on the test that or we're getting ready to take this test, that's like forever away at this point. But when we do that you would write that word down on a note card. That the key going from base whatever into base 10 is to multiply. All right, so what you're going to do first is you're going to put the numbers into expanded form. And the second thing is that you're going to multiply them out. And what I want to show you is you have already done one of these today. You did it right here. You put the number 237 into expanded form. 2 times 64 plus 3 times 8 plus 7. That's expanded form. And then you multiplied and added the results. So you've already done this. So see, you did it and you didn't even know it. So we're going to do an example. We're going to take the number 1001 in base 2 and we're going to expand it. So to expand it means that you're going to have to consider what these place values are worth in the place value system you're working in. This is base 2. So in base 2, you're going to have the ones place, because you always have the units place. And then everything is going to be powers of 2, because it's base 2. So you've got the ones place, and then you've got the 2's place, and then you have 2 squared and 2 cubed. If this were the 7's, you'd have the 7's place, and the 7 squared and the 7 cubed. If it were the 12's, you'd have the 12's and the 12 squareds and the 12 cubed, which we'll do on the second problem, but not today. And then in each of these place values, you've got the numbers 1, 0, 0, and 1. So you're going to take 1 times 2 cubed plus 0 times 2 squared plus 0 times 2. I know those zeros are not real, useful, but they're still there. And then 1 times 1. So what's 2 cubed? 8. What's 2 squared, just for the sake of having done it? 4. And then we have the 0 times 2 and 1 times 1. At some point, you're going to use your calculator, or you're going to do this one because it's not very difficult in your head. You're going to multiply, you're going to add, and what are you going to get for this digit, or for this value? 9. It's just addition. You were trying to put it in the values, but no, we're just adding. 8 times 1 is 8. These are zeros, they go away, and then plus the 1 at the end is 9. This value is 9. And we'll pick up there on Friday.